Segregated witness benefits. The segregated witness soft fork, Segwit, includes a wide range of features, many of which are highly technical. This page summarizes some of the benefits of those features. Malleability fixes. Bitcoin transactions are identified by a 64-digit hexadecimal hash called a transaction identifier, TXID, which is based on both of the coins being spent and on who will be able to spend the results of the transaction. Unfortunately, the way the TXID is calculated allows anyone to make small modifications to the transaction that will not change its meaning but will change the TXID. This is called third-party malleability. BIP62, dealing with malleability, attempted to address these issues in a piecemeal manner, but was too complicated to implement as consensus checks and has been withdrawn. For example, you could submit a transaction with TXID EF74C309 to the network, but instead find that a third party, such as a node on the network relaying your transaction, or the miner who includes your transaction in a block, modifies the transaction slightly, resulting in your transaction still spending the same coins and paying the same address, but being confirmed under the completely different TXID 683F8BFA instead. More generally, if one or more of the signers of the transaction revise their signatures, then the transaction remains valid and pays the same amounts to the same addresses, but the TXID changes completely because it incorporates the signatures. The general case of changes to signature data, but not the outputs or choice of inputs, modifying the transaction is called script-sig malleability. Segwit prevents third-party and script-sig malleability by allowing Bitcoin users to move the malleable parts of the transaction into the transaction witness and segregating the witness so that the changes to the witness does not affect the calculation of the TXID. Who benefits? Wallet authors tracking spent Bitcoins. It's easiest to monitor the status of your own outgoing transaction by simply looking them up by TXID. But in a system with third-party malleability, wallets must implement extra code to be able to deal with the changed TXIDs. Anyone spending unconfirmed transaction. If Alice pays Bob in transaction 1, Bob uses that payment to pay Charlie in transaction 2, and then Alice's payment gets malleated and confirmed with a different TXID. Then transaction 2 is now invalid and Charlie has not been paid. If Bob is trustworthy, he will reissue the payment to Charlie, but if he isn't, he can simply keep those bitcoins for himself. The Lightning Network. With third-party and script-sig malleability fixed, the Lightning Network is less complicated to implement and significantly more efficient in its use of space on the blockchain. With script-sig malleability removed, it also becomes possible to run lightweight Lightning clients that outsource monitoring the blockchain instead of each Lightning client needing to also be a full Bitcoin node. Anyone using the blockchain, smart contracts today such as micropayment channels and anticipated new smart contracts become less complicated to design, understand, and monitor. Note, Segwit transactions only avoid malleability if all their inputs are Segwit spends, either directly or via a backwards compatible Segwit P2SH address. Linear scaling of SigHash operations. A major problem with simple approaches to increasing the Bitcoin block size is that for certain transactions, signature hashing scales quadratically rather than linear. In essence, doubling the size of transaction increases can double both the number of signature operations and the amount of data that has to be hashed for each of those signatures to be verified. This has been seen in the wild, where an individual block requires 25 seconds to validate, and maliciously designed transactions could take over 3 minutes. Segwit resolves this by changing the calculation of the transaction hash for signatures so that each byte of a transaction only needs to be hashed at most twice. This provides the same functionality more efficiently so that large transactions can still be generated without running into problems due to signature hashing, even if they are generated maliciously or much larger blocks, and therefore larger transactions are supported. Who benefits? Removing the quadratic scaling of hash data for verifying signatures makes increasing the block size safer. Doing that without also limiting transaction sizes allows Bitcoin to continue to support payments that go to or come from large groups, such as payments of mining rewards or crowdfunding services. The modified hash only applies to signature operations initiated from witness data, so signature operations from the base block will continue to require lower limits. Signing of input values. When a hardware wallet signs a transaction, it can easily verify the total amount being spent, but can only safely determine the fee by having a full copy of all the input transactions being spent, and must hash each of those to ensure it is not being fed false data. Since the individual transactions can be up to 1 megabyte in size, this is not necessarily a cheap operation, even if the transaction being signed itself is quite small. Segwit resolves this by explicitly hashing the input value. This means that a hardware wallet can simply be given the transaction hash, index, and value and told what public key was used, and can safely sign the spending transaction no matter how large or complicated the transaction being spent was. Who benefits? Manufacturers and users of hardware wallets are the obvious beneficiaries. However, this likely also makes it much easier to safely use Bitcoin in small embedded devices for Internet of Things applications. This benefit is only available when spending transactions sent to Segwit-enabled addresses or Segwit via P2SH addresses. Increased security for multisig via pay-to-script hash. Multisig payments currently use P2SH, which is secured by the 160-bit hash 160 algorithm, RIP-EMD of SHA-256. However, if one of the signers wishes to steal all the funds, they can find a collision between a valid address as part of a multisig script and a script that simply pays them all the funds with only 80 bits, 2 to the 80th worth of work, which is already within the realm of possibility for an extremely well-resourced attacker. For comparison, at a sustained 1 exahash/second, the Bitcoin mining network does 80 bits worth of work every 2 weeks. Segwit resolves this by using hash 160 only for payments direct to a single public key, where this sort of attack is useless, while using 256-bit SHA-256 hashes for payments to a script hash. Who benefits? Everyone paying to multisig or smart contracts via Segwit benefits from the extra security provided for scripts. Script versioning. Changes to Bitcoin's script allow for both improved security and improved functionality. However, the design of script only allows backwards compatible soft forking changes to be implemented by replacing one of the 10 extra op-nop codes with a new opcode that can conditionally fail the script but which otherwise does nothing. This is sufficient for many changes, such as introducing a new signature method or a feature like opcltv, check lock time verify, but it is both slightly hacky. For example, opcltv usually has to be accompanied by an op drop and cannot be used to enable even features as simple as joining two strings. Segwit resolved this by including a version number for scripts so that additional opcodes that would have required a hard fork to be used in non-Segwit transactions can instead be supported by simply increasing the script version. Who benefits? Easier changes to script opcodes will make advanced scripting in Bitcoin easier. This includes changes such as introducing Schnorr signatures, using key recovery to shrink signature sizes, supporting sidechains, or creating even smarter contracts by using Merkleized abstract syntax trees and other research-level ideas. Reducing UTXO growth. The unspent transaction output UTXO database is maintained by each validating Bitcoin node in order to determine whether new transactions are valid or fraudulent. For efficient operation of the network, this database needs to be very quick to query and modify and should ideally be able to fit in main memory, RAM, so keeping the database's size in bytes as small as possible is valuable. This becomes more difficult as Bitcoin grows, as each new user must have at least one UTXO entry of their own, and will prefer having multiple entries to help improve their privacy and flexibility, or to provide as backing for payment channels or other smart contracts. Segwit improves the situation here by making signature data, which does not impact the UTXO set size, cost 75% less than data that does impact the UTXO set size. This is expected to encourage users to favor the use of transactions that minimize input on the UTXO set in order to minimize fees, and to encourage developers to design smart contracts and new features in a way that will also minimize the impact on the UTXO set. Because Segwit is a soft forking change and does not increase the base block size, the worst case growth rate of the UTXO set stays the same. Who benefits? Reduced UTXO growth will benefit miners, businesses, and users who run full nodes, which in turn helps maintain the current security of the Bitcoin network as more users enter the system. Users and developers who help minimize the growth of the UTXO set will benefit from lower fees compared to those who ignore the impact of their transactions on UTX growth. Efficiency gains when not verifying signatures. Signatures for historical transactions may be less interesting than signatures for future transactions. For example, Bitcoin Core does not check signatures for transactions prior to the most recent checkpoint by default, and some SPV clients simply don't check signatures themselves at all, trusting that has already been done by miners or other nodes. At present, however, signature data is an integral part of the transaction and must be present in order to calculate the transaction hash. Segregating the signature data allows nodes that aren't interested in signature data to prune it from the disk or to avoid downloading it in the first place, saving resources. Who benefits? As more transactions use Segwit addresses, people running pruned or SPV nodes will be able to operate with less bandwidth and disk space. Block capacity/size increases. Since old nodes will only download the witness stripped block, they only enforce the 1 megabyte block size limit rule on that data. New nodes, which understand the full block with witness data, are therefore free to replace this limit with a new one, allowing for larger block sizes. Segregated witness therefore takes advantage of this opportunity to raise the block size limit to nearly 4 megabyte, and adds a new cost limit to ensure blocks remain balanced in their resource use. This effectively results in an effective limit closer to 1.6 to 2 megabyte. Who benefits? People who run upgraded wallets will be able to take advantage of the increased block size by moving signatures to the witness section of the transaction. Moving towards a single combined block limit. Currently, there are two consensus enforced limits on block size. The block can be no larger than 1 megabyte, and independently, there can be no more than 20,000 signature checks performed across the transactions in the block. Finding the most profitable set of transactions to include in a block given a single limit is an instance of the knapsack problem, which can be easily solved almost perfectly with a simple greedy algorithm. However, adding the second constraint makes finding a good solution very hard in some cases, and this theoretical problem has been exploited in practice to force blocks to be mined at a size well below capacity. It is not possible to solve this problem without either a hard fork or substantially decreasing the block size. Since Segwit can't fix the problem, it settles on not making it worse. In particular, rather than introducing an independent limit for the segregated witness data, instead a single limit is applied to the weighted sum of the UTXO data and the witness data, allowing both to be limited simultaneously as a combined entity. Who benefits? Ultimately, miners will benefit if a future hard fork that changes the block capacity limit to be a single weighted sum of parameters. For example, 50 times SIGOPS plus 4 times base data plus 1 times witness data is less than 10 megabyte. This lets miners easily and accurately fill blocks while maximizing fee income, and that will benefit users by allowing them to more reliably calculate the appropriate fee needed for their transaction to be mined.